In this lecture video, we're going to look at classical probability and the properties it possesses. We'll start off by reviewing the definition of classical probability. We'll present 6 properties possessed by classical probability, and then we'll give detailed proofs of all 6 properties. Once we've done that, we'll list the general steps that we've been using in proving properties possessed by classical probability. So let's review the definition of classical probability. The classical probability of an event is defined as the ratio of the number of cases favorable to the event to the total number of cases. Let A be an event. Define the following notation. Cap n sub A represents the number of cases favorable to the event A, and cap n without a subscript denotes the total number of cases. Using this notation, the classical probability of A, denoted P of A, is defined as the ratio of cap n sub A over cap n. Now note that I'm using capital N in this notation, and I'm doing this because for a given situation, the numbers of cases do not vary. They're fixed for a given situation. Next, let's look at properties possessed by classical probability. Let A and B be events with corresponding probabilities based on the classical approach. The following properties hold under the classical approach. Property 1 says that the probability of any event is always between 0 and 1 inclusive. Probabilities are never less than 0 and they're never greater than 1. Property 2 says that if the occurrence of the event A implies the occurrence of the event B, then the probability of A can be no larger than the probability of B. That is, the probability of A must be less than or equal to the probability of B. Property 3 says that for any 2 events A and B, the probability of the composite event A or B is equal to the probability of A plus the probability of B minus the probability of the composite event A and B. Now again, this first composite event, A and then a V-like symbol and then B, this is the event that at least one of A or B occurs. That V symbol is a logical connective that represents the inclusive OR and is read OR. The second composite event, A and B, is the event that both A and B occur, and this symbol, called a wedge symbol, is a logical connective that represents conjunction and is therefore read AND. And so we can read this as the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Now this result is true for any 2 events A and B, and therefore is called the general addition rule. Property 4 says that if A and B are mutually exclusive events, that is, they cannot occur simultaneously or at the same time, then the probability of A or B is equal to the probability of A plus the probability of B. This is called the special addition rule, and it's a special case of the general addition rule where A and B are mutually exclusive. Property 5 says that for any 2 events A and B, the probability of A or B occurring is less than or equal to the probability of A plus the probability of B. This result is called the Bonferroni inequality, and it has useful applications in the context of hypothesis testing when we have multiple tests going on and we want to control the overall type 1 error rate. And to do that, one approach is to use the Bonferroni adjustment, which is based on the Bonferroni inequality. Next, let's look at property 6. Now let A be any event. The complement of A is the event that A does not occur, and this is denoted by A with a C in the superscript. Property 6 says that the sum of the probability that A occurs and the probability that A does not occur is equal to 1. that is, the probability of A plus the probability of the complement of A, will always be equal to 1. This result is known as the complement rule, and it's a very, very useful probability rule. Note that you often see this written as the probability of a complement equal to 1 minus the probability of A. All right, now let's prove each of these probability properties. Let's first prove property 1. So again, property 1 says that for any event A, the probability of A is always between 0 and 1 inclusive. Let A be an arbitrary event. Let cap n sub A denote the number of cases favorable to the event A, and let cap n without a subscript denote the total number of cases. Now, it's clear that the number of cases favorable to the event is an integer, and in particular, it's a non-negative integer. It certainly can't be less than 0 because we're counting things. And it's also clear that this number cannot exceed the total number of cases. We express this in the following way. Cap n sub A is greater than or equal to 0, and it's less than or equal to cap n. Dividing through these inequalities by cap n gives the related set of inequalities, the ratio cap n sub A over cap n being greater than or equal to 0 and less than or equal to 1. Now, by the classical definition of probability, the ratio cap n sub A over n is the probability of A. And so we can substitute the probability of A for that ratio in the previous set of inequalities, and so we get the probability of A is greater than or equal to 0 and less than or equal to 1. As the event A was arbitrary, it follows that this property holds for all events. Next, let's look at a proof of property 2. Again, property 2 says if the occurrence of the event A implies the occurrence of the event B, then the probability of the event A can be no greater than the probability of the event B. Expressed notationally, we write it this way. The probability of A is less than or equal to the probability of B. So let A and B be events such that the occurrence of A implies the occurrence of B. Let cap n sub A denote the number of cases favorable to the event A. Let cap n sub B denote the number of cases favorable to the event B. And let cap n denote the total number of cases. Since the occurrence of A implies the occurrence of B, it's clear that the number of cases favorable to the event A can be no greater than the number of cases favorable to the event B, since whenever A occurs, B also occurs, and B may occur if A does not. And so this implies that cap n sub A is less than or equal to cap n sub B. Dividing both sides of this inequality by the total number of cases, n gives the following inequality. Cap n sub A over n is less than or equal to cap n sub B divided by n. By the classical definition of probability, that first ratio, cap n sub A over cap n, is just the probability of A, and the second ratio, cap n sub B over cap n, is equal to the probability of B. And so it follows that the probability of A is less than or equal to the probability of B. And that's what we were setting out to show. Next, let's look at a proof of property 3. Property 3 says that for any two events A and B, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Now for a proof, let A and B be any events, and define the following notation. Cap n sub A represents the number of outcomes in which the event A occurs. Cap n sub B is the number of outcomes in which the event B occurs. Cap n sub A and B is the number of outcomes in which both A and B occur. Cap n sub A or B is the number of outcomes in which at least one of A or B occurs. And finally, cap n is the total number of outcomes. Note that the outcomes in which both A and B occur are accounted for in both cap n sub A and cap n sub B. Therefore, if we add cap n sub A and cap n sub B together, the outcomes in which both A and B occur are counted twice. Therefore, to count the number of outcomes in which at least one of A or B occurs, we can first add cap n sub A and cap n sub B together, but then we must subtract out cap n sub A and B so that that number is counted only once. In other words, we have this equality. Cap n sub A or B is equal to cap n sub A plus cap n sub B minus cap n sub A and B. Dividing both sides of this equation by the total number of outcomes cap n gives the equation cap n sub A or B over cap n being equal to cap n sub A over n plus cap n sub B over n minus cap n sub A and B over n. By the definition of classical probability, the ratio cap n sub A or B over cap n is the probability of A or B. The ratio cap n sub A over cap n is equal to the probability of A. The ratio cap n sub B over cap n is the probability of B. And the ratio cap n sub A and B over n is equal to the probability of A and B. And so substituting these probabilities into their appropriate locations in the previous equation gives the equation the probability of A or B equal to the probability of A plus the probability of B minus the probability of A and B. And that's what we set out to prove. Next, let's prove property 4. Property 4 says that if A and B are mutually exclusive events, that is, they cannot occur together, then the probability that at least one of the two occurs is equal to the probability of A plus the probability of B. Since A and B are mutually exclusive, it is necessarily the case that cap n sub A and B, which is the number of outcomes in which both A and B occur, that number is equal to 0. If we divide both sides of this equation by the total number of cases, cap n, we get cap n sub A and B over cap n being equal to 0. By the definition of classical probability, the ratio cap n sub A and B over cap n is the probability of A and B. And so it follows that the probability of A and B is equal to 0. Now from property 3, which we have already proven, we know that for all events A and B, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. If we substitute 0 in for the probability of A and B into this equation, we get this simplified equation, which says that the probability of A or B is equal to the probability of A plus the probability of B, as desired. Moving on, we'll prove property 5. Property 5 says that for any two events A and B, the probability of A or B is no more than the probability of A plus the probability of B. Now from property 1, we know that the probability of A and B is greater than or equal to 0. Let's add to each side of that inequality the probability of A or B. And so we get the inequality, the probability of A or B, being less than or equal to the probability of A or B plus the probability of A and B. Now from property 3, again which we've already proven, we know that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And so substituting this expression for the probability of A or B into the right-hand side of the previous inequality, we get the probability of A or B being less than or equal to the probability of A plus the probability of B minus the probability of A and B, and then plus the probability of A and B. And so the negative probability A and B and the positive probability of A and B cancel out. And so this simplifies to the probability of A or B being less than or equal to the probability of A plus the probability of B, as desired. Finally, let's prove property 6. Property 6 says that the sum of the probability that the event A occurs and the probability that the event A does not occur is equal to 1. Notationally, the probability of A plus the probability of the complement of A will always be equal to 1. Well, to prove this, let cap n sub A denote the number of outcomes in which A occurs. Let cap n sub A complement denote the number of outcomes in which A does not occur. and then finally cap n be the total number of outcomes. Now, for a particular outcome, either A occurs or it does not occur. In other words, either A occurs or its complement, A complement, occurs. This implies that cap n sub A plus cap n sub A complement will always be equal to the total number of outcomes, cap n. Dividing both sides of this equation by cap n gives the equation cap n sub A over cap n plus cap n sub A complement over cap n. That's equal to 1. Now, by the definition of classical probability, the ratio cap n sub A over cap n is equal to the probability of A, and the ratio cap n sub A complement over cap n, that is equal to the probability of A complement. And so we can substitute those probabilities into the equation above, and we get the probability of A plus the probability of A complement being equal to 1. And that's always going to be the case. Now that we've gone through these proofs, let's look at the general steps that we've gone through in doing each of the proofs. Step 1 was to define notation for the total number of outcomes and the number of outcomes favorable to each of the events involved in the property. The second step was to identify an equation or inequality or set of inequalities relating these numbers and then express the relationships using the notation defined in step 1. Step 3, we divide the quantities in the relationship by the total number of outcomes, cap n. We then apply the definition of classical probability to obtain the probabilities for the events involved in the relationship. We then substitute the probabilities thus obtained into the relationship involving the ratios to obtain the desired property. Now note that once a property has been proven, it can be used in proving subsequent properties. And we did this in a few of the proofs. So let's summarize what we've done. We reviewed the definition of classical probability. We presented 6 properties possessed by classical probability. We gave detailed proofs of all 6 properties using an approach based specifically on classical probability. We identified and listed the general steps involved in proving properties possessed by classical probability. So that wraps it up for now. I'll see you in the next lecture video.